at the end of the presentation. My research, just a general picture about my research, it lies in the intersection of risk analysis, statistical and machine learning, optimization, and natural hazards. And the focus of my research is to combine statistical learning and optimization to better understand and solve important problems related to power outages caused by weather events. And in this presentation, I'm going to explain one of the projects that I recently have been working on it, and it's now under review, and that one is the adaptive two-stage Bayesian model averaging for estimating the impact of hazards on power system service. So in the next slides, I'm gonna go in detail to this project. First of all, because my research is in power outage predictive modeling, and I'm going to explain about the importance of this problem and the importance of developing predictive models for the utility companies. Then I will explain in detail the model we have developed in this project, and also I will explain the case study that we apply our methodology on, and finally I will finish the presentation by the results and then summary and conclusion section. So actually, all of us have experienced power outages, but the thing is that it becomes unpleasant when it becomes longer and longer, and this happens a lot when a severe weather event like a hurricane or a thunderstorm happens. So I wanted to just start with asking a question from audience that, can you just please use the chat bar and share with us the longest time you have ever experienced power outage? I appreciate if you can do that, because I think it would be interesting for everyone. You can see the okay. I can see that, yes, we have something. 20 minutes, good. Much longer than that. 3 hours, 8 hours, 2 hours, okay, and 12 hours, the longest, 10 hours, yes. But all of them less than a day, right? Actually, severe weather events like hurricanes and thunderstorms, thanks for sharing your experience, but extreme weather events like hurricanes and thunderstorms are potential to cause damages to the power system, and outages lasting from a few hours that we saw has happened for most of us until several days. And I know someone who experienced 2 weeks of not having power, especially if you're living in the southeast of US, which experienced a lot of hurricanes. So we see that this is actually very important for the utility companies, and they invest a lot of money on it. From one of the utility companies that we're working with, it's about $10 million per day for storm days. It's cost for doing the restoration, and also between $1 to $4 billion they invest every year for tree trimming, just to reduce the actually the size of power outages. So we see that it's these are actually just the financial effects of power outages. So having some work to reduce the length of power outages can have a significant impact, and that's what I'm trying to do. Actually, utility companies, they cannot prevent the outages completely, even if they become very prepared, but they can reduce the effect of outages if they are well prepared before the event, before the extreme weather event. So what utility companies are doing, as you see in these figures and videos, is that based on the estimates that they have about the impact of weather event on the disastrous area, they call for all of the resources that they may need, and they stage them in some areas. And then once actually the storm or the hurricane hit the locations, they send out the resources, the utility personnel, and all the repair vehicles to these locations to start doing the restoration as fast as possible to just reduce the lengths of power outages. And in this process, having a predictive model estimating the impact of power outages in advance of a weather event is a key component for all of the decisions that are made in the utility companies. So in this regard, we see that what we are doing is that initially it starts with collecting the data. So here's actually how we see the problem, and it's about, I wanted to explain where does the predictive modeling problem fit within this larger area. So it starts with collecting the data. We need to collect data, and we collect, some of it is public data, some others are utility specific data, and also we need to collect data about the geographical variables, environmental variables, and weather data, and we need to do the cleaning process, everything. And once we have the clean data that we can develop our models, we do testing and training, and finally a predictive model is developed, and that one we run it before the events, and the results are pops up on the website of the utility company as provided for them. And then based on like the results of these predictive modeling, they make the decisions about vehicle routing, about resource allocation, about job scheduling. So having an accurate model predicting the outages before the weather event is very important for the utility companies. And in this study, we are developing a model for predicting outages accurately. To review the literature very briefly, we see that studying the literature from just the modeling perspective, we see that there's a lot of different models developed in the literature, and they started with parametric statistical models like GLM or GAM, and then non-parametric and ensemble models like random forest and boosting got gained more popularity, and for years these two types of models were the most accurate ones. But then in the recent years, the zero inflation issue received more interest, and two-stage and multi-stage models were developed. So studying the literature, we see that there's a process that are used for developing the model. And actually, this is not specific to outage predictive modeling. In many different predictive modeling problems, we see that this same process is used, and that's actually for developing the model, we initially start with a number of candidate models. Then these models are trained on the data, and we compare the models with each other based on some performance metrics. And finally, we select the best model. And once we select the best model, that model is represented as a model formulating the process. So, from that point, we ignore all the uncertainty that exists about the modeling. So we do all of the inferences, all the variable importance, everything based on that selected model that we're not sure about. And in some cases, this selected model might be slightly more accurate than others. So the weakness of this process, this predictive modeling approach, is that we ignore the model uncertainty. And when we ignore the model uncertainty, the decision makers may make riskier decisions. And the thing is that the previous data that we have for training the models, it may not be sufficient for training the best model. And so over time, when we get more data, we may find that, okay, a model that we rejected initially might be the best one, and it's not coherent, especially for the decision makers to choose a model which was previously rejected. And also, in many problems, predictive modeling, accuracy of the predictions is much more important than the type of model, whether it's a boosting model or it's an parametric statistical model like GLM. We care about the accuracy of prediction. So all of these things actually make us to think about another type of modeling approach that we use in our study. The other thing is that we're going to develop a model which produce probabilistic predictions, meaning that the output of the models is probability distributions instead of just point estimates. And finally, we're going to develop a model which make predictions for different types of weather events, not being specific for hurricanes. Yes, so in this study, actually, we're going to develop a model which is adaptive, which is learning over time. And we're not going to select one specific model. Actually, so we assume that we have multiple models. And in this case, we assume that the multiple models that we have are M1, M2 to MK. And where each of these models make predictions, and we're going to combine the predictions of these models with each other. And also, to make the model more accurate, we assume that data that we have is not one Chekhov data. We have data which is coming from multiple clusters. And our goal is to combine the predictions of these models with each other based on some weights. And that these weights and the models are updating over time. So in the first step, here we see that P of y given x is actually the probability distribution that we're going to estimate. Y is the response variable and x is the covariates that we have. And by just applying the law of total probability and conditioning, because we have multiple clusters, by conditioning on the cluster that the record is coming from, we can derive the first formula. So probability distribution of y is equal to probability distribution of y, knowing that this record belongs to a specific cluster times multiplied by the probability that that record belongs to that specific cluster. Then in the next step, actually, so in the first step, we're considering the multiple clusters that we have. In the next step, we know that we have multiple models and we're going to combine their predictions. So another time, we're going to apply this law of total probability and we condition it on the models. In this time, actually, probability distribution of response variable is equal to the sum of probability distributions produced by each of the models that we have, weighted by some values. And these values are what we're going to estimate. To estimate the weights, actually, we formulated with a multinomial logistic regression because we know that the output of multinomial logistic regression is multivariate binary values. So it's actually a model formulating which of these base learners that we have making the best prediction for a specific record. So we model the weights with a multinomial logistic regression. And from now on, our goal is to estimate the parameters of this multinomial logistic regression model. So to estimate the bold capital B is actually the matrix of parameters in the multinomial logistic regression, and we're going to estimate it using the maximum a posteriori approach. So we know that it's proportional to multiplication of the likelihood and the prior. And for our case, we assume that the prior of the parameters of the multinomial logistic regression has a Gaussian distribution, which is actually not unusual. And also we can derive the likelihood of the parameters using the formula for the multinomial logistic regression. But the thing is that even by knowing the prior and the likelihood, the posterior distribution does not have a closed form. An exact inference for the posterior distribution of parameters is intractable, so we need to approximate it. And we're going to approximate these parameters using a Laplace approximation method. So in the Laplace approximation method, actually, we assume that the parameters have a distribution, and this distribution is shown with psi of b, and we can derive actually an approximation for this distribution, which is shown in this formula based on the Laplace approximation. And we know that here, if we choose b hat such that the first derivative of the psi function is 0 at this point, then the posterior distribution of b can be approximated with a Gaussian distribution with the mean of b hat and the variance of the second derivative of the psi function as a function of b. So now we know that the parameters of the multinomial logistic regression can be estimated by a Gaussian distribution, and the problem is reduced to just estimate the b hat, which can be done using any optimization method. And because here we are going to learn it over time, we use the stochastic gradient ascent optimization method for learning the parameters of learning this b hat for solving this optimization problem. So far, we explained that how the weights of the base learners are updating over time. And now, actually, we're also going to update the base learners that we have. So we assume that each of the base learners, the models M1 to MK, has a training set. And whenever we receive a new record, each of these models make predictions, and the new record is added to the training set of model making the best prediction. And then periodically, when we receive like enough data, we retrain the model on the training set, and so the models become updated as well over time. So this figure actually summarizes the algorithm. So in the first step, we have a number of base learners, M1 to MK, and the output of these base learners is some probability distributions. And also, we have a multinomial logit model, which estimates the weight of each of these base learners. We know the weights, we know the probability distributions coming from each of the base learners, so we can combine them with each other and produce one single probability distribution as a forecast for the covariate X that we have. After that, we receive more data, and so we can update the base learners, and these base learners are substituted with the initial base learner that we had. So this figure shows the total algorithm that we have. We applied our methodology on a customer interruption data that we received it from the American Electric Power, which is a really large utility company in the US. And we had the data from 2012 to 2019, daily customer outage data for 46 districts that you can see them on the right figure. 46 districts in 4 states, Indiana, Michigan, Ohio, and Texas. We had some covariates, and the covariates are divided into 2 types, static and dynamic covariates. The static covariates are the covariates representing the power system, like the number of poles, number of transformers, conductors, these kind of variables that are not changing over time. And we also have dynamic variables like the weather forecast, wind gust speed, probability of having thunderstorm, information about soil moisture, standard precipitation, and these information we know that they're dynamic, they change from one day to another. And because in our algorithm, we assume that we have multiple clusters. So initially using the static variables that we have, we divided data into 6 clusters. And this number 6 is coming because we found it optimal based on the CH measure. So we divide data into 6 clusters, and we derived 24 different base learners based on the data that we have. And these models are different from each other based on quantile regression forest, Bayesian linear model, Bayesian cart, and BART model. So we have 24 different base learners and data which is divided into 6 clusters, and we're going to now apply our algorithm on the data. Yes.
تقالات جيب 0.75 واقل.
Excuse me, I think we have
لا
some
لازم في
noise.
تقالات تلاقي 0.75.
Okay, we should be good now.
Okay, thank you. Okay, so actually that was the data that we have, and we're going to do holdout analysis to test our algorithm. To do holdout analysis, first of all, we take data 1 month out to test the result, the final model on the test set. And then the rest of the data that we have, we provide this data gradually to the model, because our model is learning over time. So we're not going to provide all the data to the algorithm once. So we provide data to the algorithm day by day, and every day when we receive more data, our algorithm, based on the accuracy of predictions for the new data, the weights become updated. And also after a month, after receiving data of 30 months, because we have enough data, then the base learners get updated based on the updated training sets that we have. So this slide shows actually the accuracy of our algorithm. As I said, the algorithm is updating over time. So the x-axis in this figure shows the iterations, the days of data that we have. And then the y-axis is the continuous rank probability score, which is a score, an extension of mean absolute error for the case when we have probabilistic predictions. But the lower CRPS is the better. So we see that our algorithm over time, its prediction for the test set is becoming better and better. We have different colors because for like every 30 records, which shows data of 1 month, has the same color. And we see that over time, the colors are changing because every month we update our algorithm. We wanted to see what percentage of the improvement is because of model updating and what percentage is because of weight updating. And we found that 89% of improvement in the CRPS is due to model updating, and 11% is due to weight updating. So both of the things we're doing for improving the model are working well. And also, in addition to checking the performance of model over time, we compared the accuracy of model with the base learners, because we have some models. We wanted to see what's the performance of our algorithm based on like these 24 base learners. And we see that both based on both continuous rank probability score and also mean absolute error, the accuracy of the Bayesian BMA model, which is the first box plot in the plot, is better than any of the base learners. So we find that we have an algorithm which is able to combine predictions of these base learners with each other in a way that the accuracy of the final output is less than others. The accuracy is more than others. And also in addition to providing more accurate predictions, one good property of this algorithm is that it actually can tell us under which conditions, which model is working well. For example, here, you see that there's a lot of numbers. I definitely don't want to go through all of them, but the main point is that here, these numbers are the the parameters of the multinomial logistic regression that we trained in this process. And the higher the parameters for each of the variables shows that that model makes better predictions for higher values of these variables. For example, we see that model number 1, which was a quantile regression forest type of model, make better predictions for the case when we have like high probabilities of hail and tornadoes. So we know that under these conditions, model 1 is making better predictions. So actually, our algorithm is able to tell us that each of these models is making better predictions under some specific conditions. I'm going to end with the summary and concluding remarks about this algorithm that we developed. So we see that we have developed an algorithm which is able to learn over time. And this is very practical for the utility companies because usually we provide them with a model. And then once the contract is over, then no improvement is made on the model. But with this algorithm, actually, it's useful for the utility companies because they can start running the model, and as new data is coming, this model become updated and updated over time. And also, the accuracy of the model is more than the base learner. So if we choose the base learner in a good way, if the base learners are good models, then we know that the prediction of our model is even better. And finally, it provides a lot of insights about the initial models for us that, for example, for wind events, which model is better? It's a linear model or it's a BART model. So it can tell us which model formulate the process better under any specific condition. Okay, and that was it about my presentation. So thanks for staying with us and welcome. Please ask any questions that you have about the method or about this project.
Hi, Elnaz, can you hear me?
Yes.
Thank you so much for your speech. And it's very impressive. And I just have 2 questions. The first one is, why did you choose the 2-stage model? I mean, and what are the 2 stages you mean here? And the second one is, what is the greatest change you face during the time you are doing all the projects?
Sorry, your first question was that
why did you choose the 2-stage model instead of you? As you mentioned before, I saw that you also mentioned there were a multi-stage model as well. So I want to know, why did you choose the 2-stage model?
Okay, sure. Actually, the 2-stage and multi-stage models are some other models in the literature. I was telling that for dealing with the zero inflation issue in the literature, 2-stage and multi-stage models are developed, but actually I don't call the model that I've developed in this project as a 2-stage model. It's actually an adaptive model, and everything is just, we have one model adapting over time based on the data. So it's actually not a 2-stage model. Oh. But yeah, I don't know if I answer your questions.
Yes, definitely. Thank you so much.
No problem. And also you had another question, the second one.
Yes, so what is the biggest change you face during the whole process you finish the project?
The challenge.
Oh,
the challenge.
Difficulty.
Yes.
Or difficulty.
Yes. Okay, there's actually a lot, yes, because I've been working in this area for all my PhD. There was a lot of challenges. There's a lot of challenges regarding the data, because there's always a lot of uncertainty in the data. And especially when we're aggregating the data, for example, we are making prediction for district levels. This is one of the challenges I always have, and I'm thinking that in the future I should work in this area. And that one is that when we are making prediction for the district level, we aggregate data to the district level, but actually we know that we can, for example, if we're going to estimate one variable like total rain for the district level, what we're going to report for the total rain. Is it the mean total rain? Is it the max, a standard deviation, or how we can reduce the amount of uncertainty that we have regarding the data? That's one of the challenges that I would like to in the future work in this area. And the other thing is that when we develop the model, presenting the results for the utility companies, because the main customer of our models are utility companies, and it's useful when they can use our models in an optimal way. So presenting the results and just explaining what the results are and how they can use it in a best way is one of the other challenges we're dealing in this area.
Okay, thank you so much. I appreciate your answers.
Oh,
thank you.
Thanks for your question. I can see the chat room. Is there any questions there? No. So any other questions?
Hi, this is John Reeves. I have a quick question.
Sure.
But first, nice presentation. Thanks for sharing, and thanks Professor Cash for organizing the seminar. Kind of related to Manfred's question, are you comparing these your results with any other baseline model? Probably missed that, but besides your base learners, are you using other model? Are you comparing with other models?
Yes, that's a great question. Actually, we are going to do that. We haven't done, so I don't have any results, but that's definitely because we have in the literature, there are different models. And for example, I know from the literature that quantile regression forest, random forest, and these models are able to formulate the problems better than others. So that's why I'm choosing this type of model as the base learner, and I'm comparing my model with the base learner. But yes, I haven't so far compared it with like some other models in the literature, but it's our plan. We will do that. Yeah, thanks for asking.
Okay, yeah, sure. No, thanks. Thank you for sharing.
Hi. Oh, sorry.
Sure.
Hi, Elnaz. Can I ask one question not related with the speech?
Sure.
I mean, I also searched your file. I think you had really a great profile over the past few years in your PhD. So I want to know that can you share with us about your experience in doing a reviewer job of some journals? Did it cost your time, and is it difficult?
Sorry, your voice is choppy. So can you?
Oh yes, sorry. Can you hear me better now?
Just the last part. The question about the department.
Yes, and you did the job as the reviewer for some journals. I want to know that was it difficult, and did it cost your time, and how was the experience for you?
The experience of reviewing papers for journals.
Yes.
Oh, sure. Actually, it started from for me, it happened after I published my first paper. So you receive like requests from that journal, and over PhD this happens that for example, if the editors of some journals know you, they know that your research is related to some area, so they send you papers for review. And if you have published papers in some specific journals, then you receive more papers for them. But at the beginning, I should say that at the beginning, it's a slow process. you see that maybe in a year you receive 1 or 2 requests for reviewing papers, but over time, when you do a good job in this process, you receive more and more requests, and then you should decide whether you're going to review for some specific journals or not.
Okay, thank you so much.
Oh, no problem. But definitely Professor Barker is much more experienced in this area, and please share your experience with us if.
Well, I mean, if you are someone who's wanting to review for journals, then I would probably tell your advisor that, because so what I've done with some of my students in the past is I would maybe decline a review, but recommend my student to do it. And so if your advisor knows that you want that experience and that you work together, maybe to work on reviews or something like that,
okay,
you know, that could get your foot in the door.
okay,
Yes.
Thank you.
And one thing, Poplons, I've been using it for some years. I think it's a good thing because even if you haven't done any previous reviews, you can upload your information there. You can have an account, and then this can help like other reviewers to know you and your research areas better.
Okay, sounds great. Thank you so much for the advice. Thank you.
So how long have you been a PhD student, Elnaz?
Oh, this is my 5th year. So I should defend in, this summer or at the beginning of fall, and then, yes.
So I can't remember, forgive me, do you have a job lined up yet?
Oh, no, I wasn't in the job market last year. So my plan, the previous plan was to be on the job market. I will be doing the postdoc for the next year. My plan was to be on the job market this coming fall 2020, before all of these things about the pandemic, but maybe we should delay it for another year. Yeah, I don't know whether there will still exist any.
Yes, I think currently the job hunting, the job market is definitely influenced by the pandemic, right? You can't see too many jobs posting there, right?
Yeah.
Mm-hmm.
Yeah, well, yeah. So there's going to be, I would anticipate there's going to be a pretty big dip in jobs that are going to be available for a start for fall 2021. So you're just going to stay at Michigan then?
Yes.
Okay. Okay, well, best of luck on that. Any other questions?
You.
Thanks again. Thank you. Have a wonderful day.
Much. Yeah, thank you very much.
Okay. Well, have a good rest of the summer, and tell everyone to join in on these Wednesday calls. We'd love to have even more folks show up.
Yes, this is really nice. Thank you. Bye.
Sure. Thank you. Bye. Thanks, Professor Barker. Yeah.
Absolutely.